Okay, this is going to be in two parts. One of them is sort of basic, and it's about the relation between information and the things about it that Shannon and Turing didn't realize, with a little bit of introduction for people who are new to this field of quantum computing. So it's going to be some very low level things that might be very familiar to people who are involved in quantum computing. But I try to take a broad perspective on it. And then the second part is going to be about what I think is a neglected area, which is to understand the thermodynamics of not only of computing, which is, I think, is well understood in a certain limit, but the thermodynamics of error correction, or in other words, of fault-tolerant computing, which I think is an area that needs some more research. And so actually, these are two separate talks that I didn't actually merge into one. So we're going to start with talking about information, reversibility, and the thermodynamics of fault tolerance. But first, I'm going to talk about what's different about information from the metaphors that people use for it. And we have nowadays, we talk about number crunching and the idea of information as a commodity was really launched by Shannon when he came up with a way of, I mean, the most amazing thing was that they be able to talk about communication without even talking about meaning, but about, in his 1948 paper, came up with a really convincing way of quantifying it. So we talk about information as like a commodity, like as in the original idea of computing by Babbage. The data was called the memory was called the store, and the processor was called the mill. So we were sort of thinking of data as grain. Now, so although our information revolution, which is still going on, is based on these two great abstractions from the 20th century, there was a little bit of stuff that these two guys, or they and their collaborators and their colleagues of not just these two people, of course, that they left out. And you might say they left out, and Landauer, my mentor, would have said they left out some physics, but I think it'd be more appropriate to say that they left out some essentially mathematical ideas in physics, which were absent from for example, Turing's notion of computation. And these were the two ideas were reversibility and, of course, quantum superposition. But in contrast to the way people think about information, it's really different from anything material. And one of the easiest demonstrations of this is that it doesn't flow like oil or gas or water. And here's a simple example: the butterfly network. If I'm trying to get some red data from here to here, and at the same time some green data from here to here, I can't do it. And the places that I can send it along are marked by these black lines. I can't do it. I get a bottleneck or a blockage here if I try to do that, if it's a material commodity. But if it's data, no problem. I just take the red data in here, I make one copy, send it here, send the other copy there, do an XOR here, same thing with the green data, and then we get everything out. It does what it does. So it doesn't flow like ordinary stuff. Now, of course, the history of science is full of people who imagined something they were trying to understand behaved like flowing water or flowing some material substance, like the caloric of thermodynamics, which didn't work because it wasn't quite right. Now, because of so even classical information doesn't behave like a stuff. But quantum information is worse or better. Where do I get this? Yes. Oh, and I should say, yes, here's some, these are some of the earliest work in quantum information done really around the same time as Halevo's early work, but not published until much later, was from Stephen Wiesner. And he showed the inadequacy of the Shannon notions because he came up with two tasks that can't even be really described and certainly not accomplished in the Shannon theory. And that is combining two messages into a quantum signal from which the receiver can receive either one, but not both. But by receiving one, they spoil their ability to receive the other. I'll talk about that later. And the other is the quantum money that's physically impossible to counterfeit, which is really the earliest appreciation of the importance of the quantum no cloning principle. Now, this is what I always say to people when I'm trying to explain quantum information. I say that everybody understands classical information, but quantum information is like the information in a dream. If you try to describe your dream to someone, your memory of it changes and you only remember what you said about it, you don't remember the dream. But unlike dreams, it follows well understood physical mathematical laws. And at the risk of boring most of you or some of you, I try to put it in the form that is most concise and least mathematical, but still mathematical enough to be correct. The quantum information in one slide is superposition principle. That is, between any two reliably distinguishable states, there are intermediate states that are not reliably distinguishable from either one. And the way these intermediate states behave is like directions in a three-dimensional space, more precisely, rays in an n-dimensional Hilbert space. Any direction is a possible state, but the only states are only reliably distinguishable if the directions are orthogonal. In the closed systems, time evolution conserves this distinguishability. In other words, it's a rigid rotation. And in an open system, the distinguishability may decrease, but never increase. So, and for the newcomers to quantum information, this is nicely illustrated by the behavior of polarized photons. So if I have a perspective view of a calcite crystal and horizontal photons coming into it, they all go through in a straight line. But if I send vertical photons, that is not vertical with respect to the surface of the Earth, but vertical with respect to the axis of the crystal, they'll be shifted as they're passing through the crystal and come out. And this means you can use each one of them to carry a bit of information reliably. But if they're polarized at an intermediate angle, they, instead of being shifted by an intermediate amount, they behave unpredictably and come out in the top beam with cosine squared theta and the bottom with sine squared theta probability. This is the fundamental, one of the many equivalent fundamental manifestations of quantum unpredictability, which makes philosophers and people who devise different interpretations of quantum mechanics scratch their head for now it's getting about nearly a century. Well, so leaving aside what this all means for a moment, it means that you can use vertical and horizontal photons to carry reliable bits, and left and right diagonal photons to carry reliable bits, but you can't use all four kinds, and no measurement can distinguish all four kinds. And this is not a limitation of a particular measuring apparatus, as it would be in a classical system, but it's a fundamental consequence of the laws of quantum mechanics, giving rise to the possibility of quantum money and quantum cryptography. And I like to say, before explaining it, where it comes from, Bill Wooters, who has been teaching undergraduates for many decades, likes to explain it by way of a pedagogic analogy with one of those old-fashioned schools where the students were not supposed to ask questions or volunteer information, but just respond to the teacher's questions. And so the teacher says, "Are you vertical or horizontal?" And the student says, 55 degrees. "I believe I asked you a question. Are you vertical or horizontal?" "Horizontal, sir." "Did you ever have any other polarization?" "No, sir, I was always horizontal." So then that's one of the things about quantum mechanics that Einstein didn't like. And we'll talk about it a bit later, I think. So there's no way around it. If you could clone photons, then you could measure them reliably. And if you try to clone a photon by sending it into an ideal laser, the output will be brighter, but it will be noisier, and just to a degree that's necessary to keep it from being any more useful to find out what the original polarization was. So this is the thing that Wiesner used to prove the possibility of money that is physically impossible to counterfeit. And it was, this isn't his picture of it. This is sort of fanciful picture that we made of a quantum banknote with 20 polarized photons in perfectly reflective boxes. And then this led to a very similar idea, but more useful, which was quantum cryptography, quantum key distribution. And this is the original apparatus that Gilles Brassard and I and our students used. It's a piece of lab equipment made by theorists. Well, getting back to the basic principles, I think the insight that came from this work that really waited for both Shannon and Turing after quantum mechanics had already been understood and thought about by physicists a lot, was that there was a similarity between the way quantum systems behave and the way classical information behaves. So that just as all classical information processing is reducible to the manipulation of bits by logic operations that operate on them only 1 and 2 at a time, so this is also true of quantum information. But of course, the most fascinating and manifestation of quantum information is entanglement. And it arises naturally during interaction by virtue of the superposition principle. So I said, for example, I'm going to talk about the interaction of 2 qubits. And as we said, that any quantum processing of quantum data can be understood in this kind of diagram that's the quantum analog of the I wouldn't call them circuit diagrams because they don't actually have voltages and grounds and capacitors in them. They're an idealization of that kind of circuit diagram that's used in computer science, where what flows along the wires are bits, and what interrupts the wires are logic gates, where the bits are subjected to operations such as AND and NOT and XOR. Well, for quantum information, we have this fundamental, the only 2 qubit operation that we need is this exclusive or controlled NOT, which flips the target qubit to the orthogonal state, rotates it 90 degrees. If the control qubit is vertical and doesn't do anything to it if it's horizontal, and because it's a quantum gate, if you give it a superposition of inputs, it gives you a superposition of outputs, and this is already an entangled state, which is, as we like to point out, and as has been already pointed out, it's not the same as any a product state of the 2 qubits. It's a state in which the 2, in this case, this is one of the triplet states. In terms of linear polarization, they have the same linear polarization, even though neither one has a linear polarization at all. And it's certainly not the same as both of them being diagonal. And going on and trying to explain this to lay audience, or like at a dinner party, I say it's a little bit like my experience as a young man in the summer of love in 1967 in San Francisco, where you could run into people who felt they were in perfect harmony with one another, even though they didn't have any firm opinion about anything. And now we know that this was not very rigorous mathematically. The hippies thought that with enough LSD, everybody could be in perfect harmony with everyone else. But now we know that entanglement is monogamous, and I'll speak a little bit more about that. But the more entangled two systems are with each other, the less entangled they can be with anything else. So what do we use entanglement for? Now, this is one of the more spectacular things about that you can do with entanglement. If you want to take, because of the no cloning principle, if somebody gives you a qubit or a photon, say, of unknown polarization at the lower left here or down here, and wants you to produce a photon of the same polarization somewhere else, you have a problem, because if you try to measure this photon's polarization, you will disturb it. And then the best that you can do is to send some partial information. You're in the position of somebody who's trying to counterfeit the quantum money, and you will get something that has some chance of being wrong here as your would-be copy of this photon. So it seemed that you can't. It looks like you're asking an impossible job, but in fact, it's possible using entanglement. We start off with a state to be teleported. We take an entangled pair of particles, like in the state that I just showed you, and then we do here a joint measurement, which essentially is you're asking these two photons, don't tell us anything about yourself, tell us what you have a choice. Are you in a singlet state, or what? And if not, which of the three triplet states are you in? And then from that answer, we can take the other as yet unused entangled particle, having spoiled those two, and take that classical information and correct the state of that to produce an exact copy of this, in principle, exact copy of this one, which has been destroyed in the sending process. So it seems then that if you say, well, what happened to looking at this through the information lens, what happened to the information in this photon? It's a funny kind of information. It's quantum information. It's information that we can't really get out of it in a classical form without spoiling it. But somehow we can get it from this photon over into this photon. And how did it go? Well, part of it went through this classical message, which by itself has no correlation with this initial photon state. This is just an equiprobable distribution over a 4-letter alphabet. So what we'd have to say is that the part of the information that didn't go this way went this way. In other words, it went backwards in time. So it seems that in quantum mechanics, information can not only flow through a bottleneck for a classical commodity, it can even flow backward in time without breaking any laws of physics. So our original intuitions about information need to be tempered somewhat. And so there's, in the presence of entanglement, we can use two classical bits. Ooh, what did I do here? You can use two classical bits to send. You can use two classical bits to send one qubit from here to here, or you can use one qubit to send two classical bits from there to there. So in the presence of unlimited entanglement, two qubits are as good as, two classical bits are as equivalent to one qubit. And we actually, if you go back to the original picture we had here of the butterfly graph, if you try to ask what's the quantum butterfly theorem for qubits instead of bits, if we had a qubit coming in here, we'd have a problem here because we're asking to clone it, and you can't clone a qubit. So in fact, the butterfly graph doesn't work as a way of getting double the capacity, the throughput for qubits the way it does for bits, But if you give each of the if you give each of these nodes an unlimited amount of entanglement with each of the other nodes, they can dispense with sending qubits and send everything as classical bits and get back that same advantage. So it's a very powerful resource, even though it has no ability to communicate by itself. Okay, so yes, this is teleportation. Okay, now I'm speaking about the monogamy of entanglement, and this is again an explanation of it at the dinner party level. So it sort of fits with the saying about human relations that 2 is a couple and 3 is a crowd. And then suppose Alice and Bob would like to get entangled, and they do that by that circuit that I just showed you. And then Bob likes being entangled, and he's foolish enough to try to also become entangled with somebody else. And as soon as he does that, his entanglement with Alice is spoiled, and he doesn't get any more than correlated classical randomness with Judy, his other girlfriend. And then, but of course, the whole 3-qubit quantum system is still in a pure state. So what that means that is if one of Bob's girlfriends leaves, he will only be correlated, classically correlated with the other one. But if they both stick around, he's perfectly entangled, not with either one, but with the non-trivial relationship between them. And this was actually foreseen by a novel by Colette in 1922, which she probably thought didn't have anything to do with quantum theory. And this is the entanglement in the monogamy of it is the reason that entanglement wasn't discovered until the 20th century. And it is because we live in an atypical part of the universe in which parts of the universe, especially photons from the sun, interact with the world that we're in a way that commutes, and they are initially out of equilibrium. And this is the situation which gives rise to what Zurich and Bloom-Kohut call quantum Darwinism, but I think should be called quantum spam. And this is where a system is being continually observed, interacting in a commuting fashion with systems that are out of equilibrium and don't interact later. And this means that because of monogamy, the one aspect of the information in the system is massively amplified and at the point of obfuscating the others. So the system is classically correlated with all of these parts of the environment in one degree of freedom, but in the complementary or conjugate degree of freedom, it's entangled only with the whole environment. And so this gives us a way of explaining, or at least it's an explanation that I think it should even satisfy people who are more followers of Copenhagen interpretation than in many worlds. But it explains or begins clarifying the origins of quantum randomness. And that is that I wasn't really telling you the truth when I said that the photons going into the crystal randomly choose whether to become vertical or horizontal. Because if you don't measure them, this behavior, what I called random behavior, it can be undone. And so in a sense, it's not really behavior at all. Nobody looked at it. And you can put the beams back together by rotating all the vertical ones to horizontal and the horizontal ones to vertical. And they'll come out, they will re-remember the polarization that they would have lost if you'd measured them. So if you want to put that in terms of the Bill Woders's pedagogic analogy, you would say that what makes the pupil forget his polarization is having to say it in front of the whole class. And if you get the whole class to undo their learning what his polarization was, he would get it back himself. So this is the program of quantum information, I think, is a successful program which says we take the whole classical theory that Shannon and Turing developed, and we say that it's a special case of quantum information where a classical bit is a qubit with one of two more or less arbitrarily chosen orthogonal values. Classical wire is a quantum channel that conducts them faithfully but randomizes their superpositions. And that happens because the wire interacts with its environment, and the environment acquires a copy of it if it was 0 or 1, and otherwise becomes entangled with it. And so a classical channel is a quantum channel with an eavesdropper, and a classical computer is a quantum computer that has the handicap of having eavesdroppers on all its wires. So the question about how do quantum computers get their speed up if you can finally build one is, or their advantage or supremacy, it's where do classical computers get their sluggishness or their disadvantage? Okay, so now we're going to talk information theory and how the classical and quantum information theory is different. Of course, we've heard about the entropy in Shannon's information theory, which is the same function as was used in statistical physics. And the Shannon's expression for the capacity of a channel is the maximum over input distributions of the input-output mutual information. This quantity, the analog of this was discussed, the quantum analog using von Neumann entropies was discussed in 1997 by Cerf and Adami, but they were not sure exactly what it meant in terms of operations on information. That became clearer later. But for the Shannon's data compression theorem, is to source coding, there is a direct quantum analog, and it says that you can take a bunch do a block code on a bunch of photons. Let's say these photons come from a source that emits two non-orthogonal states. It's no vertical photons, just diagonal and horizontal ones. So this says these input letters, although they're independent and identically distributed, they're of less than maximal entropy because the diagonal state is not reliably distinguishable from the horizontal state. And so the fact that it's less distinguishable means that this random source has less entropy and can be compressed to a smaller size by a quantum circuit, which means, let's say we run them through the quantum circuit and we concentrate all their information into some of them, throw the others away, and then top it up with horizontal photons, and coming back out doing the inverse transformation, we get an asymptotically perfect approximation to the original state that you sent in. So this is the direct analog of source coding, but it's quantum source coding, and it uses the von Neumann entropy instead of the Shannon entropy. But there is, of course, now the quantum analog of the quantum source code, channel coding, and the capacity, and this uses quantum error correcting codes, which there's been much work on. You have to use more than, this is the analog of the three-bit redundancy code. You need 5 qubits to correct a random error in any one of them. But if there's at most one error, you can undo the encoding operation. So essentially, we stake a single qubit in an arbitrary state, 4 0 qubits, and we put it into an entangled state which will withstand the corruption of any one of the 5 qubits and still get the original back. So we'll compare the quantum, the theory of quantum information to the theory of classical information. Well, classical information had only one kind of capacity, which Shannon found, but with the quantum information, we have multiple capacities. How many qubits can you send through a channel for use if you use quantum error correcting codes? What's the classical capacity of a quantum channel? You're using a quantum channel, but you're trying to send classical bits through it. I said before, you could send one bit reliably through a noiseless qubit channel, and Halevo showed that you couldn't send more than that through a single channel. There's the private capacity. And then there are various assisted capacities. We give them some resources like extra entanglement, which I mentioned already. So this is the landscape of quantum Shannon theory, and in some ways it's more complicated than classical Shannon theory because there are these multiple capacities, and several of them are not are very you can define them, but they're hard to get tractable expressions for. No single letter formula, as in the case of the Shannon capacity. Indeed, even the classical capacity of a quantum channel lacks a known single letter formula. But the entanglement assisted capacity does have a simple formula. And I would say, so that's a way in which quantum information is more complicated, but in another way, in a nice way, it's simpler than classical information theory, because classically there are distinct kinds of interactions that you cannot substitute one for another. For example, and this is especially true when I'm sitting alone in this room with my computer, if I'm a speaker and you're a member of my audience, no amount of talking by me enables you to ask me a question. But quantumly, interactions are intrinsically bidirectional. So I guess if there was a fully quantum internet, you could ask me a question through the same channel that I'm speaking to you, but I also could probably catch COVID-19 from you too. So anyway, and here's what comes out of the Shannon theory of what this says is that of these various capacities, there is one that has a really simple formula. It's the entanglement assisted capacity. So what we're talking about here, we're sending in general, some mixed state of which we have the purification. We have a pure system of which this is just one part. This part is held behind as a reference system. This one is sent through the channel and comes out there. Now the channel it can be modeled by or is equivalent to an interaction with some environment. So it just as in classical noise. But what we find out is that the entanglement assisted capacity is the maximum over input distributions of the entropy of the input plus the entropy of the output minus their joint entropy. Well, they're not both there at the same time, so we take the entropy of the reference system, which has the same density matrix as that of the input. So in other words, what Shannon discovered was an elegant formula for entanglement assisted capacity of quantum channels. But since he was thinking about classical channels, it happens to be the same as their unassisted capacity. Well, I mentioned that the imperfect distinguishability can be used for cryptography in this scenario of quantum key distribution, which is good in a classical setting where you know who your friends are, like in the Cold War era. You can cast your mind back to the Cold War. You know who your friends are and you know who your enemies are, and you outnumber your enemies. You're the one eavesdropper is trying to listen to your communication, and you trust the person you're sending to. So, of course, in the business world, nobody trusts anybody else, and so we need to have two people who are communicating with each other, but don't entirely trust each other. And that is a very important scenario, which has always been important. And what can quantum information do to help that job? Well, that is the other task that Wiesner thought of back around 1970, and that is, can you make? Actually, I think he wrote it in 1968, but it was only published into 1983. His other invention was a way of multiplexing two messages into a single physical transmission, such that reading either one message spoiled the other, And this turned out to be of considerable cryptographic importance because this, not the physical way of doing it, but the idea of that primitive, that is a channel through which you send a bit, or you send 2 bits, and the receiver can choose to receive either one but cannot receive both, is extremely practical for facilitating exactly this task I mentioned earlier of discrete negotiation between 2 mutually distrustful parties. Now, Wiesner, even in his original paper, mentioned that this was not secure in principle, only in practice, that if you had an adversary armed with a quantum computer able to store and manipulate quantum information, store it for an unlimited time, you could actually break the multiplex. And it was shown by Myers and Low and Chow that any such system could be broken in principle. But these authors also showed that if neither party can store the quantum information, technologies related to this Wiesner multiplex do provide a way of doing these provably discrete 2-party negotiation, where the security is based on laws of physics rather than on, and also the impossibility of not having a quantum computer. So this is something we would definitely sell to Gil Kalai, because he would be pretty confident that we wouldn't be able to break it. So that was pretty much the outline of the what happened in quantum computing. There were some kinds of computation which and new ones are continually being discovered that may be helpful for practical problems. Although what we're now trying to do is to find problems where, well, I could say they're already practical, not for computational problems, but for the problems in cryptography that I mentioned, the 2 problems, the problem of communicating over a channel with an eavesdropper, and if you make some rather plausible, reasonable at the current time, assumptions that nobody has a really good quantum computer, then you even have this really valuable primitive of doing 2-party discrete negotiation. But what about the whole science of computability? Well, back in 1936, Turing showed that the halting problem for the Turing machine was unsolvable, and they defined a class of problems that are equivalent to solving the halting problem. And if you try to fix that problem by giving a computer an oracle for the original halting problem, it just gets a worse halting problem, and then there's an infinite hierarchy of more and more unsolvable problems. This has been known for a long time, and there was originally some hope that I would say vain hope that quantum computers would be able to solve unsolvable problems, but they're not. They at worst are in a class smaller than exponential time for a classical computer to simulate. So in the history of the field, the focus shifted from computability to the more important problem, or the more practical problem, of tractability, with these classes like polynomial time and I said this is not R. It's supposed to be RE. RE. So polynomial time is the sort of the tractable version of computable, the baby version of computable, and non-deterministic polynomial time is analogous, somewhat analogous to the baby version of the class RE of here we go. I'm going to get this back again. Of things equivalent to a halting problem, and then there are these higher presumably harder classes, the polynomial space, the polynomial hierarchy, the polynomial time interactive proof, and the rather surprising result in 1992 that IP equals P space, so that this somewhat two-party interaction between an untrustworthy prover and a polynomially time-bounded verifier is equivalent to what a single computer can do in polynomial space with no time bound except the trivial exponential one. And now, since the 90s, there's been the attempt to understand where quantum computation fits in to this complexity zoo, as Scott Aronson calls it. But the really exciting thing that just happened in the last few months was this discovery that there was a connection between what a complexity class that you can define with the help of entanglement and the very notion of computability. So on the left, we said MIP star. That means that there are multiple entangled interacting provers working in polynomial time, and the things that they can convince Arthur of, these are the multiple Merlins, are exactly the things for which would be the halting set of a Turing machine. So this was a very deep and I would say quite unexpected connection between what looks like an exotic branch of the theory of tractable computability with the help of multiple provers and interaction, and the notion of computability. But it certainly doesn't mean that you can use a quantum computer to solve problems that a Turing machine couldn't solve. It means that the limitations that are exposed between two provers that can't communicate and are trying to convince somebody, somewhat like the two suspects being interviewed by the police in separate rooms. If they have entanglement, it complicates the kind of things that they can and can't show, to the extent that it goes all the way up into the realm of computable versus not computable. So from the lesson on this I would say of this whole subject of quantum information is that it is a better basis for the theory of communication and computing, and that the classical communication and computation theory are a useful subset of it, and new things are continuing to be discovered. And now I'm going to move on to the second part of my talk. And that is, and I think I'm running out of time here. What's the situation here? Maybe I should do this relatively quickly. Let's see. Yeah. So this will be relatively quick. So yes, I'm going to talk about toward a thermodynamics of fault-tolerant computation, and I'm going to talk about it in terms of Brownian computing, which is computers that work somewhat like the molecular apparatus that copies DNA or makes an RNA transcript of it. But this gets to the importance of entropy and Landauer's principle. And the second law is famous for having a lot of equivalent statements of it, which don't even sound like they're in the same language. This is the Kelvin statement. The first one is the Kelvin statement, which was set to music by Flanders and Swan. The Clausius statement. This is a thing that you notice if you work in baking pottery in a hot furnace. It involves ice skating, and the best statement of Landauer principle was done by Ben Schumacher. Doesn't explicitly mention Boltzmann constant or heat, or work, it just says, and it's a little bit like the Clausius statement, no physical process has as its sole result the erasure of information. And it's just equivalent to saying that the laws of physical dynamics are reversible. And entropy is something that puzzles a lot of people, especially because there's so many different ways of talking about it. The original way was from the theory of heat engines, and it was an integral over reversible path of the heat flow divided by the temperature. Then the statistical version of it is the distribution of this is the one that Shannon used, and the connection between those two is that when you compress a gas to half its volume reversibly and isothermally, you convert nkt log to bits of information into heat, because you've reduced the uncertainty of where all those atoms are. Now, the algorithmic entropy or Kolmogorov complexity, it looks like a totally different thing. It's talking about the size of the smallest computer program to cause a computer to produce X. But the connection there is that any concisely describable ensemble probability distribution has a statistical entropy that's very nearly equal to the average algorithmic entropy of its members. So algorithmic entropy or algorithmic information content is, you might say, the single element quantity, which when averaged over the whole ensemble gives the statistical entropy of the ensemble. So now we know from Landauer's principle that in principle that any computation can be done reversibly. But that really involves ideal hardware, somewhat like the hardware that people think of when they're, what was used to make Carnot's engine, where there's no friction in the lubricating fluid on the pistons, and everything goes at nearly infinitely slowly. But and all the computers that we use in the real world are like that. But if you think of reversible models of computation, there are two kinds. They're the ballistic computers, like the Fredkin and Toffoli colliding billiard balls that you can use to do universal logic. And then the Brownian computers, which I'll talk about now. This is like where individual atoms are moving with a significance. They execute a random walk in a low energy and configuration space. And so here's an example. I think I can get this to go. Yes, this is what it would look like if you could look at a stable, something that is stable because it's low energy, of a lipid bilayer immersed in separating two areas of water. And so what we have, yeah.
Sorry, Charlie.
Yeah, I think we should say this is done.
No, I'm interrupting you. Sorry, I'm being impolite here. But yeah. You have another talk on Friday, intro talk, which would be perfect.
Let me do that. So, because I'm running out of time, so why don't we just say that I'll save part B of my talk for Friday. Good, thank you. Okay, good.
Okay, so thank you very much, Charlie, for a very comprehensive, holistic overview.